Now there's a more specific addition rule. We learned before if they are mutually exclusive, then we would just say the probability of E plus the probability of F is what the probability of E or F is. If they're not mutually exclusive, much like we did for like counts in the previous chapter, if I'm looking for like the number of elements in E or F, I would usually take the number that's in E plus the number that's in F, and I would subtract away the number that are in both. Same thing here for probabilities. I'm going to do the probability of E plus the probability of F minus the probability that both occur at the same time. With all honesty, the first formula that we mentioned about mutually exclusive did not really need to be mentioned. Because technically, if they were mutually exclusive, this just becomes 0 right here, and you're left with the formula that we had in the case it was mutually exclusive. So this is the formula for describing, the possibility of two events occurring, one or the other, or both. So now, for example 4, we can make use of this to some extent because we can say, okay, well, let E and F be two events. We're going to let P of E equal 0.38, P of F equal 0.5, and the probability of E and F be 0.15. Compute the following. Well, there's a well-duh question here, a no-brainer. B, because, we told you outright what the probability of E is. It's still 0.38. As far as the probability of E or F goes, I could just use the formula that we have over here. I know, because I know the probability of E, the probability of F, and the probability of E and F. They're these. And so that's the substitution. And so when I then put them together, the probability of me being in E or F under these conditions is going to be 0.73. The probability of not F, well, there's another rule that basically says a complement. Since we know all probabilities for an event have to total 1, then if I'm doing the probability of, of a complement of an event, then I could say it's just going to be 1 minus the probability of the event occurring. So here I would do 1 minus the probability of F, which is 1 minus 0.5, which is 0.5. So in the case of D, when you start getting complements intersected with non-complements and maybe even multiple unions and intersections, here's where it's a good idea to start going back to using the Venn diagram. So I'm going to use a Venn diagram for this last part. I could probably figure out things, but then even to do that, I have to use a formula. We haven't talked about how to calculate the probability of an AND event by itself yet. And even with that, there's two ways of doing it, depending on whether or not the events are dependent or independent, and we will get into more into that later, because that's gonna hold a basis as how I calculate that. So I could do this another way that we're going to learn later, but for the time being, we'll overcome that hurdle just by using this Venn diagram, because I have information I could put in here already. Now I'm putting the probabilities in here. I know the probability for E and F is 0.15. I know that the probability of F is 0.5, so that and the 0.15 it shares with E should total 0.5, which means that the probability of being only in F is 0.35. And I could do something very similar with E. I know that I have 0.15 that's being shared with F, and since there's 0.38 total, then the part that's just in E and nothing else would be 0.23. I also know that the universal outside of the two circles is 0.27 because remember all four of these, all my probabilities together should total 1. So now I'm looking for the probability of something occurring in not in E but is in F. So I'm looking for the parts that are in F but not in E. So basically I'm looking at this region right here. And based off of that, that's probability is going to be 0.35.